that we now know how, this is amazing, we know how to look at the atmospheres of planets that are 40 light years away. We can see into their atmospheres. We can see what those atmospheres are made of. And so we can use the chemical compounds in the atmospheres that we can detect as a proxy for whether there's life or whether there's technology. So, for example, if we found oxygen in the atmosphere of a planet like the Earth, we'd be like, there's got to be a biosphere there, because if it wasn't a biosphere, all that oxygen would quickly react away. And oxygen will not stay in an Earth-like atmosphere unless life is pumping it out continuously. Likewise, if we saw something like chlorofluorocarbons, right, the stuff that we mistakenly, burped out in the atmosphere from our refrigerators and our air conditioners, if we saw a chemical like that in the atmosphere, which we could detect, we wrote a paper on this, then you would say, like, oh my God, there's technology on that planet.
Hello, everybody, and welcome back to Chasing Consciousness. So today, we have the mysterious arising of life and eventually intelligent life on our planet to try and explain, to then apply that to our search for other intelligent life in the cosmos. Now, to explain this, we're going to be getting into the coevolution of the Geosphere and the Biosphere on Earth and the feedback loops between them, the possibility of planetary intelligence, the difficulty of laying a technosphere over a geosphere and a biosphere, and the risk of civilizations wiping themselves out before they learn how to harmonize them. We're going to be looking at the changes in the search for extraterrestrial intelligence, since we can now identify potentially life-sustaining exoplanets. We're going to be looking at the changes in the search for extraterrestrial intelligence, since we can now identify potentially life-sustaining exoplanets. We're going to be looking at the search for technosignatures from advanced civilizations and the potential space junk from the many civilizations that presumably didn't make it. And we're going to be discussing recent claims of ancient and potentially even present visitations to Earth by extraterrestrial intelligence. And we're going to be getting into pushing our imagination beyond our own history of life here on Earth, given that the story may have unfolded very, very differently under different conditions elsewhere in the universe. Now, fortunately, to face these tough and complex issues, our guest today is a world specialist in astrobiology with a talent for making these topics fun and imaginative, astrophysics professor at the University of Rochester, Adam Frank. He's the author of over 200 scientific papers and 6 books for the general public, including The Blindspot and The Little Book of Aliens, which we're going to be focusing on today. Now, I have been wanting to speak to Adam ever since I first heard about his approach to considering the possible evolution of life and intelligence both on and off the Earth. So I just can't wait to get into this. So without further ado, let's go. Adam Frank, welcome to the show. Thanks for coming on. How are you today?
Real pleasure. I'm looking forward to this conversation.
Well, I really appreciate it, Adam. Now, I want to get straight into the meat of today's topics because there's so much from your work that I want to get through. But let's start with a little context from one of your most recent books, The Blindspot, which was written together with my previous guests, physicist Marcelo Gleiser and philosopher Evan Thompson. Now, both of them did a really, really good job of explaining how science has tended to surreptitiously substitute the useful method of reduction with the metaphysics of reductionism, and how science tends to undervalue human experience. Now, the obvious starting point for science is human experience, so there's no need for us to sort of go back over that. But perhaps you can tell us what drew you to this concept and to work with Marcelo and Evan, because human experience isn't often the interest of hard scientists.
Yeah, I think, this is one of those things that is temperament. The philosopher William James said that all philosophy comes down to temperament. And I think it's from when I was a kid, even. I fell in love with science when I was a little kid, fell in love with astronomy when I was 5. But I always had this sort of sense of presence. I remember being a kid and being in the backyard and, like, looking at a tree and just having a sense of the tree's aliveness, or my aliveness, with the tree, which is one of the reasons I've always had an interest in, or had a spiritual practice as well. There's always this debate in science about the split between science and religion. And of course, religion is politics. The organized religions are about politics. But the personal idea that there is, that we encounter the sacred, that we encounter the sense of more, and that's sort of fundamental to being human, is to me, that's what animated my experience of science. And that was what my first book, The Constant Fire, was about. So, experience is, and what I argued in that book also, that the human spiritual endeavor, to try and find a word that people wouldn't get pissed at me about, has always been about experience. It's not about dogma or doctrine, or it's really fundamentally, this ancient call to the world, to know the world more, to become closer to the world, is about experience, and that it's the root of both spiritual endeavor and science. Like, we come to science because we see how beautiful and extraordinary the world is, and we're moved by it, and that's the root. And so I've always felt, even though, I mean, it's not entirely true. I was a Platonist. I was a young Platonist, where I believed, like, the universe is just mathematics. And if you understand the mathematics, you're reading the mind of God. But as time went on, I lost interest in that. I saw sort of how hollow it was. That actually my own experience of the world overflowed any mathematical description I could have, any description, whether, in words, and that the only thing, actually one important part for me was poetry. I encountered poetry early on, became a fan of poetry. And I remember reading a definition of poetry was, it takes you to the boundaries between the expressible and the inexpressible. And the idea that there is the inexpressible is something that oftentimes in sort of, science, what we call scientific triumphalism, it's like there is no such thing as the inexpressible. Everything is ultimately reducible to math or whatever. And I just, by my 20s, I was really disillusioned with that idea and didn't feel it did justice to what is so extraordinary about being human in the world. So that's where it kind of started for me.
Mm. And how does this issue interface with the topic of today's interview? The way we try to understand the origin of life on Earth and the possibility of life elsewhere. Has the blind spot blinkered science in this area too?
Well, I think, when it comes to understanding life itself, what we get often is the machine metaphor. I mean, the way that science approaches life, because it didn't really have any other approach, or at least the philosophies. One of the things the point we're always making in the book, and we're making as we're going forward, is that when we talk about the blind spot, it's not a problem of science. It's a problem of a philosophy that got glued onto science, whereby people, a certain kind of advocate for science will tell you, this is what science says. Science says you are nothing but your neurons. You're a computer made out of meat in a robot gooey body. Your body is nothing but biological machinery. Every cell is just really a machine. That perspective, that life is a machine, I think is fundamentally flawed. And it's one of the reasons why we run into all these problems, why, AI has the problems it does when it tries to encounter the idea of sentience, across the board. And so this idea of understanding the importance of experience, that experience is central, gives you a different way of approaching the problem of life, which I think is also, first of all, if you want to understand the problem of life, which I've now become very interested in, not just as an astrobiologist, but as a physicist. We have this grant from the Templeton Foundation to study what's called semantic information. And it's the idea that basically what makes a cell different from a rock is the use of information. Life uses information, and in that way is an agent. It is an autonomous agent, and that is unlike anything we've ever described before. It's not robots. The best robot we could come up with is not an autonomous agent because we program it. Somehow life is self-organizing, creates its own goals, is an autonomous actor in its own world. And that is really a very different way to look at life. I think it's a way that science can approach life, but it's also going to, in doing so, and this is the point about the blind spot, we're going to need a new conception of nature. The idea that nature is just out there, independent of us, and that we're not even players in the story of our description of nature is, I think, fundamentally flawed. And it's why you get the problems in quantum mechanics, you get problems in cognition theory, all of these paradoxes that people end up in these what I call them, sort of philosophical or conceptual yoga positions, right? They end up straining themselves, like the many worlds interpretation, which tries to deal with quantum mechanics and the problems of measurement and the observer in quantum mechanics by positing an infinite number of unobservable worlds, right? That is a intellectual yoga position. So yeah, a lot of this comes down to the inability to really sort of own up to the sort of chicken and egg problem, the circularity, the need to jump into the circle of in understanding life, rather than starting from mathematical propositions and then deriving your way mechanically to some sort of mechanical view of what life is.
And we get deeply into this, listeners, with Evan Thompson in the Embodied Cognition interview. Obviously, the co-author on the blind spot with Adam and with Marcelo. So do recommend Evan's talk on that. Now, you've said in the past that materialism alone cannot solve the mystery of consciousness. And it just sort of bumped around in my head. I mean, that is saying a lot, because most hired scientists tend to say there is no mystery of consciousness at all. It can just all be attributed to brain activity in the service of homeostasis, basic survival. So
Right.
what is the mystery from your point of view? I mean, is it the arising of autonomous agency that you just mentioned? What does materialism need assistance from to get to grips with the
The
mystery?
fundamental mystery is the verb to be, right? And that's where like no account of a materialistic account of the of life or of the universe itself can get to. It's all dead matter. There's no verb to be in it. We as sentient experiencing agents, or even I'm already being so scientific by saying agents. I mean, you have to step all the way back and ask fundamentally, where does any of this begin, right? It doesn't begin with the Big Bang. It begins with you are alive. You find yourself in this world, right? You're already embedded in this world. Every morning you wake up, it's there. It doesn't go away until you die, and then who the hell knows what goes on? You can't get rid of it. And that also you're part of a community. The community already had to be there. You didn't just show up by yourself. You were already part of a community of sentient life. And so the idea that like materialism, which is really so far downstream from that. First, you already have to be in the world as a experiencing agent who is part of a community of language users, or you couldn't even express the idea of materialism. There's like 10,000 steps downward, down the chain from that, including you have to be part of a community that has sort of formulated ideas about, science. We can investigate the world in this way, and then we'll form, communities, and we'll maybe build laboratories. So the idea that these abstractions, like materialism is an abstraction that you must first be experiencing, enmeshed. You must find yourself in the verb to be. And then you build these abstractions like materialism and the mathematics that goes along with, Newtonian mechanics, etc. And then, the idea that you're going to take from that thin abstraction. I mean, it's beautiful and it's powerful and it needs an account. Like what I mean by that is that the mathematics, say, the formal systems of mathematics that we use to describe particles and their motion, amazing, needs an account of why it works. But the idea that you're going to be able to take that abstraction and somehow, which you purposely pushed experience out of to try and make it universal, and that you're going to be able to take that thin skeletal abstraction and stuff back into it the infinite richness, the holism, the indivisible holism that is your experience, my experience, that you're going to be able to stuff that back into the idea of materialism, I think is the fatal flaw. That experience always overflows your descriptions of experience. And this is a point It's certainly there in a lot of spiritual traditions. It's there and it's deep in Zen. And I have to, I always have to come clean and say I've been a Zen practitioner for 30 years. So I'm kind of steeped in that. But even in philosophy, in Western certain branches of Western philosophy, even Wittgenstein, and I think it's the seventh proposition, says that which cannot be said, we must pass over. And a lot of philosophers said, "Oh, well, we're just not supposed to talk about that stuff." Instead of focusing on like, "Oh, there's a whole part of being alive which we can't say. What do we do with the stuff that we can't say? Ignoring it is not the answer, but acknowledging it and acknowledging that the stuff we can talk about requires as a precondition that there's the stuff that you can't say. There's just this raw, the verb to be. And just to close this out, even Stephen Hawking recognized this, who was the materialist, when he said, what is the fire that burns in the equations, right? Like what animates these equations, and so even he recognized that, like, right, these are beautiful equations that I, as a theoretical physicist, am in love with, that, they are a pale, pale reflection of the richness of the actual experienced world.
Wow. Adam, I'm not going to add to that because there is just so beautiful as setting a context coming from a hard scientist and a theoretical physicist. That is a beautiful way of entering into this quite complex conversation. So before we get on to the astrobiology and estimating the probabilities of life elsewhere, let's first just have a quick look at the arising of life on Earth, because it is literally the only example we have to project how it might have worked on other planets. Now, can you start with that point, Adam, that despite this really high probability of intelligent life elsewhere, because the universe is so vast, we still have the statistical issue that for now we only have one example of complex life evolving. Why is that significant for our analysis?
Well, it's interesting. So let me just go step a little bit back. I mean, we don't really know that the probability of life or intelligence is high. We know there's squizillions of planets, right? But, that doesn't tell you that the probability of life is high. Like, for example, if I have a trillion planets, but when I go through all the physics and the chemistry and the blah, 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 and I find out that the odds of forming life on any of those trillion planets, that's a lot of planets, is 1/2 trillion, right? Then I'm SOL, right? I'm out of luck because I just ran out of planets. So there's always this thing that, we all have this intuition. I do as well. That my God, there's so many planets. There's so many galaxies. I was just looking at this beautiful image, or was an animation that where somebody was zooming through the DESI data. This is this new mapping of the universe, and there's like trillions of galaxies, and they're just zooming through the map, and you realize every one of those galaxies has 400 billion stars, right? So yeah, the numbers they're stunning, but it is possible. It is entirely possible that whatever mechanisms, I'm using that again. I noticed that even I just use that word mechanism. Okay, fine. Let's understand that sometimes we fall into that language, but let's be careful about our taking the metaphor of that language too far. But whatever mechanism generates life and intelligence, it could just be very rare. Now, I don't believe that's true. I that's my belief. I have no evidence for that, but so let's take the idea of like, okay, we only have one example so far. What do we do with that? Like, how do we deal with that? Now, there are some really clever ways of using examples where you have just like a little bit of data to be able to infer something bigger. So this is often falls under what is called Bayesian reasoning. It's a way of dealing with probabilities when instead of thinking about probabilities in what's called a frequentist way of viewing it, we're like, oh, I do 100 experiments and how many turn out positive, how many turn out negative. Bayesian reasoning thinks about probability in terms of updating your information, right? So here's a great example of Bayesian reasoning. You're in a new town, you've never been there before. You're walking down the street and you see the number 20 bus go by, right? Bayesian reasoning sort of gets you to go like, oh, there's a bus 1 through 19 probably from that, right? You only got one piece of information, but it allowed you to like go further than that. So people like David Kipping, who is one of a younger astrobiologist whose work I really love, he really has used this a lot, and particularly has done work trying to understand how we use the fact that we're the only life we see, but we also know that life on Earth appeared really early. right? So the planet has been inhabited for approximately 4 billion years. There's some argument there about exactly, but it turns out that the planet, it was only about a half a billion years after the planet formed that life showed up, or almost as soon as life could form, it did. So does that mean that life is really common? And he's done some work that sort of indicates that, yeah, you can take that piece of data to say that not intelligence, but life at least may be easy to make.
Hmm. Okay, well, let's start at the start with the geosphere. What are, in theory, the ingredients necessary in rocks flying around through space to foster life? And what are the competing theories on that first magical step that brought it to Earth?
Yeah. So I'm going to give you the standard account, and I'm happy with the standard account, except for that question of agency, because I do really
Which
think.
we're going to come back to. Don't you worry.
Right, right. Because I do think that there's a certain way. I mean, the standard view is that it's easy to see how all the ingredients for life are there on a planet, and I, in general, agree with that. But I still think, from a theoretical perspective, it's the because we don't understand agency, we don't understand autonomous agency. But let's just say that step eventually will be worked out, or it'll be worked out to the degree that we believe we understand it enough, even if we couldn't make it happen in a lab or we couldn't reproduce it in a computer. So, what you really need is for the planet to have, before life starts, to have a sort of geochemical cycling, a geochemical richness that sort of allows the conditions for life to arise. And what do I mean by that? One thing that's really interesting is that minerals evolve. Like, it takes a while to get, so minerals are just basically rocks, but rocks, and there's lots of different ways you can put together silicon, magnesium, and other things for them to form these solid compounds. And it turns out that probably you need enough mineral evolution to allow then those minerals to act as a substrate, perhaps, for life to form. So there's actually got to be some planetary evolution that has to happen before you even get to life. And so what do you need? A planet needs to have an atmosphere, right? Needs a bunch of, as you said, the geospheres. It's got to have systems, even abiological, non-biological systems that are interacting. So things like an atmosphere, a layer of gases, a hydrosphere, liquids. Doesn't have to be water. I mean, I said hydro, it's water, but water is just so good at doing what life needs that probably, I mean, water is so abundant. So probably a liquid water, a lot of liquid water, maybe ice, a cryosphere, and then what we call the lithosphere or the geosphere, which is the top layer of rock. And all of those have to go through their own kind of evolution, probably before you can get life to happen. So that's why, Sarah Walker will often talk about that a planet has to be ready for life. And then David Grinspoon, I love, he said this idea that life doesn't happen on a planet, it happens to a planet. Because once you get life started, and this is the Gaia hypothesis, it probably needs to, if it's going to be around for a long time, take over, needs to rapidly hijack those systems. The biosphere emerges, it becomes its own system on top of the atmosphere, cryosphere, hydrosphere, and it just hijacks them for its own good and manages then to keep the planet in conditions that allow it to remain habitable.
And that's exactly what I wanted to talk about next, because you draw attention to this, and so does Sarah, actually, to the codependent evolution of the geosphere and the biosphere.
Right.
Which we might not immediately think of because we tend to sort of see these spheres as layered on top of each other.
Right.
But actually, it's true that the biosphere, when it lays on top of the geosphere, it really points towards this highly integrated co-evolution between the two. Can you sort of maybe just give us a few examples of how actually these two came to co-regulate each other and co-influence each other really quite quickly?
Well, the best example of this, the uber or example of this, is the evolution of an oxygen atmosphere. Right, when the Earth first formed, the atmosphere was pretty much nitrogen and carbon dioxide. There was almost no oxygen in the atmosphere, and critters emerged. You got single-celled creatures; they were going about their business, and they figured out photosynthesis pretty quickly. But the kind of photosynthesis they had developed required, it only happened in the oceans. It required iron ions to actually work. And so it was limited. If you didn't have ions in the ocean, you just couldn't get more energy out of light. And then somewhere after about 1 billion years, some critters figured out how to like scaffold a bunch of different pieces of chemical shenanigans together to create a photosynthesis that used water. Right? It would take water, break it apart, take the hydrogen, use that to go through its little dance and make a sugar molecule, right? And then the oxygen got farted out. The oxygen, got spit out. And very quickly, this became so successful, and all these critters were using it that the air started to fill up with oxygen, right? And so, at around 2.5 billion years ago, we have what's called the Great Oxidation Event or oxygenation event, and the oxygen levels climb. And then later on, they'll climb again. And that changed the entire chemistry of the planet. Every aspect of the planet shifted because life created the oxygen atmosphere. So that's just like, and we wouldn't be here, right? You think of all the other changes. But the ozone layer, which actually keeps ultraviolet radiation from hitting the ground, right? That wouldn't be there without. So thinking out so many different ways in which life has changed the planet.
And so you call these things Gaian feedback loops, as we see this geosphere and the biosphere co-regulating each other. And we tend to think about Gaia theory as more of a claim about planetary agency or consciousness. Can you just tell us, Adam, why these feedback loops can sort of maybe deepen our understanding of Lovelock's theory and help us understand this more his idea about inherent intelligence in this complex system rather than some sort of, person?
Right. So, it's Lovelock and Margulis, Lynn Margulis, who was, because Lovelock was a chemist, really, by training, brilliant. But, he teamed up with Lynn Margulis, who was a biologist who really understood the global microbial ecosphere or biosphere. And she was the one who brought some essential ideas to the table, one of which was autopoiesis, the idea that a system life is always autopoietic, meaning it's always self-regulating and it's self-creating and self-maintaining. And her idea was, she was the one who sort of was able to get them past this idea that, like, oh, Gaia theory assumes the planet is alive or conscious. It's not conscious. It's a system that is a complex system that has this quality of being that has agency, right? It doesn't necessarily have self-consciousness, doesn't even have consciousness at all, but it is autopoietic in that it is self-creating and self-regulating, and therefore this is something we're really interested in and trying to study. You can describe it as being an agent. So it's all these webs, right? What all these feedbacks? What is it that allows the biosphere to to impose regulation on planetary conditions like temperature and humidity and other things like that? It's a zillion feedbacks between microbes and the atmosphere, oceans and the microbes, and then once you start getting more complex forms of life, you can think of the ecosystems in a lake, forests, and the mountains, and it's just like an infinite web of these feedback loops that together form the autopoietic system. And so Sarah and David Grinspoon and I wrote a paper a couple years ago called Planetary Intelligence. And what we were arguing for, eventually we wanted to get to the technosphere, what we've built recently. But we started off with the biosphere, and we said, look, that rich, dense tapestry of feedbacks that form the biosphere, we should think of that as a kind of intelligence or a kind of cognition, right? It's a self-regulating, self-adaptive system. And that it works towards its own benefits. Like, it is autopoietic in the sense that if the planet undergoes a perturbation, like a giant comet hits, the systems will try and pull that perturbation back and pull the system back to the state where, the planet remains habitable. And one of the things we argued was that the technosphere, i.e., the climate change that we're driving, et cetera, the technosphere is not autopoietic, and we don't have planetary intelligence in that way. And so we were using the biosphere and a Gaian model for the biosphere to actually project forward to what we need to do with the technosphere so that human civilization is still here 10,000 years from now.
And this is the work you've been doing, as you said, with Sarah. And who's the other co-author there?
David Grinspoon.
David Grinspoon.
He's also an astrobiologist. Yeah, great
So
guy.
I just want to zoom in on this idea for a moment, because it seems quite controversial, but actually it's really, really logical. This idea that intelligence is the intelligence of a planetary scale process. And this is a topic that we talked about with Evan as well, about cognitive systems in life. And in that interview, he said, and this is a quote, "Mind is a systemic property or process. So not just localized in the brain, but distributed." Obviously, that's referring to humans. But it's interesting. He was talking about this very close interrelationship with the environment and with the rest of our bodies, not just the mind itself. So in that sense, you're seeing planetary intelligence as a sort of the interaction of all of these various components that allow it to regulate itself. But you're saying that's not autonomous agency, that it's not that the planet is choosing to do that. The intelligence required to do that is distributed in the entire system. Is that right?
Yeah, and I think that's actually it's I don't think well it may be an agent. It may, or let me put this, it may be useful to describe it as an agent because it will respond to perturbations. Like it knows that there's a perturbation, knows in the sense that all of those feedback webs represent a kind of sensorium that it then responds to. Like, it's aware of its own state in that sense, right? There's no consciousness there. It's not like I am Gaia, Earth Mother, and now I shall, in my beneficence, change the oxygen levels. But it's more that and this. Let me step back. This goes to this different conception of what we mean by life. That it's not just and even intelligence. It's not just in your head. It's always distributed among among communities. Right now, again, no one is saying that a planet is self-conscious or that's even really conscious. But there's ways in which, as we broaden our understanding of what we mean by these concepts, that sentience, right? Evan, has written on this. The idea that sentience goes all the way down. Even the simplest cell should be considered sentience in that it has what he calls fab, feeling alive being. It's the feeling of being alive, right?
Cellular cognition. Cellular cognition. Michael Levin's work is exploding across this. Finally, biology is catching up.
Right. Yeah. And so, now again, to what degree do we want to ascribe that to a planet as a whole? I don't know. But I think there are ways, and this is a project we just recently actually wrote a paper on taking a first step to applying this semantic information theory to the simplest model of the biosphere, which is what is called Daisy World. So I think it's a fruitful way of thinking about things because we got to break out of this idea, which is just like so, 17th or 18th century, 19th century Europe, that, life is just a machine. It's just a bunch of gears and cogs. And have this, broader sort of fluid understanding, which I think is really emerging out of the whole study of complex systems. So David Krakauer, who is one of my favorite complex systems guys, he's the head of Santa Fe Institute. And he wrote a really interesting paper called An Information Theoretic View of Individuality. And it was a way of looking at, what's an individual and what's not. And it's a fascinating idea because, a cell in your liver, on one level, it's an individual, right? It's actually operating, it's got its own operation, internal sensors, systems, etc. But it's part of the liver, and the liver is not an individual. It's your liver. But then again, so you're an individual, but you're also part of a society, right? In which case you're not an individual anymore. You're part of something larger. So there's this kind of fluidity of individuality. And that, at some sense, the proper unit for thinking about life, and this takes us to the question of astrobiology, the unit is really the biosphere. It's the biosphere that is sort of what we should think about as the base level of life. And then everything else ends up being subcommunities within that. So this question of distributed cognition, I think, is fascinating. And we know there's distributed cognition in microbes, right? What's called quorum sensing with bacteria. And it goes all the and eusocial organisms like ants and termites, etc., and the famous naked mole rat. But even forests now, there's this debate about whether forests, through the fungal networks that link their roots, that even they may have distributed cognition, pushing resources to distant parts of the forest that are under stress. So again, this sort of idea that the brain, or that intelligence, sentience is in the head, and nowhere else, that this is just a computer, really, I think is so fundamentally flawed, and so fundamentally comes from taking the current technology that you're using too seriously. And that, which has always happened, right? People in this, originally in 1700s, minds were clocks, and then minds became steam engines, and then minds became, electric circuits. And so it's just, I mean, we keep
But
making the same
that's
stupid mistake.
understandable. That's understandable. We use our analogies to describe what we see going on out in the real world. But my question here is, obviously this is already quite controversial, looking at intelligence in this distributed system sort of sense. But what about this correlation between intelligence and mind? Let's take the analogy of the human body as a collective of cellular cognitive subsystems. Like we said, listeners, the Michael Levin work is really finally starting to have ripples in biology.
Yeah.
People are really starting to take on the fact that even a single cell that moves away from a toxin or move towards something that it can metabolize has some form of cognition, and in that sense, some form of agency.
Yeah.
So
Yeah.
we imagine this huge collective of cellular subsystems in our own body, each with its own agency and cognition within the larger system. And as it gets larger at each stage, each of those forms a little self, which presumably has its own sense of cognition, of agency. So why is it so weird to say that that is a form of mind, that liver has its own mind within its own experience of what it is to be regulating its cognition and regulating its system? This could go up to ecosystems, as you just mentioned, maybe entire biospheres, right up to planets and stars, right?
Well, I mean, I think, a star. So this is the interesting question. Like,
Galaxies, the entire cosmos.
well, yeah, right. But then that's
That's
making
a
a
system.
leap. Yeah. Well, listen, well, it's not a complex adaptive system, right? Everything you did up until you got to a star can be a biosphere is a complex adaptive system. That's why I'm in love with this science right now. I'm on sabbatical now, and I'm just spending the entire time reading everything I can about the history of complex adaptive systems. So
But a
complex
star is
adaptive.
not like that.
No, a star. Here's the thing about a star. Let me tell you. So this is my joke that I use all the time, right? If you gave me the initial conditions of a star, you said, okay, here's a star. It's got this much mass. It's got this composition of hydrogen, helium, blah, blah, blah. I can pretty much tell you everything that's going to happen in that to the star, that entire life, billions of years. Like, not every detail is like which flare happens on Thursday, but I can tell you how it's going to die. It's going to be a black hole or a white dwarf. Totally can nail that. Now give me a cell, right? An amoeba or a single celled animal, and say, well, what's going to happen with that in 4 billion years? I would never, ever be able to predict a giant kangaroo that would, or a giant rabbit that would punch you in the face, right? Which is a kangaroo. So, evolution is open ended. Complex adaptive systems have this weird quality of being able to invent, to go past themselves, to innovate.
And
And
the key
that is
here is biosphere. The key here is biological system.
Yeah, is that you have to initiate. That's why I think, even though, I think we're making progress to understanding how the basic idea of life comes together. I still think that agency part is really how this open-endedness initiates. That there's going to be, I think, on some level, there's going to have to be, and we're already seeing it, like you're pointing out with Levin and such. There's going to have to be a real fundamental reimagination of what we mean by nature, and that takes us all the way back to experience, right? Because we always want to do, when you thought about the star, right? What we did, both of us did, is we did that third person view, that God's eye view. We imagined ourselves floating out in space, right? And looking down on the star as if we weren't there. We're looking down on the star, but we're not actually there, right? And science, by the way science evolved out of the 17th century, was that God's eye view was literally instantiated as the ideal, right? And it literally was the God's eye view, because Newton was explicit about this in the Scholium. And when he was trying to found his ideas of absolute space and absolute time, he actually references God as kind of like the frame in which you can have this disembodied view from nowhere, which is what the philosopher Nagel calls it. So so this is how we get back to experience. There is no view from nowhere, right? There is no view of the star that just is disembodied and floating around there. We are the ones in our experience who parse the world into, from like, seeing the sun, seeing the stars, then building telescopes that enlarge our experience. All of that occurs, all of that you need experience. You need to be an experiencing agent embedded with all the other experiencing agents, part of the biosphere, for any of that to make any sense. So, in some sense, it all starts with life. It doesn't start with the Big Bang. It starts with life in its world, parsing, sort of dividing up self and world, having that make sense, and then drawing theories, starting to conceptualize it. But it's all embedded. You can't unembed it from experience. And so that's what I mean about, in order to really tackle this, we're going to need a new conception of nature, not one that, it starts with that disembodied view, because that disembodied view is very useful, but it's a fiction. It's a kind of fantasy that's useful for doing a certain kind of science. But once you push further, you can't hold on to that anymore.
But that experience question brings us back to mind. And how do we separate the idea of planetary cognition, agency, and intelligence from the idea of planetary consciousness? I mean, are you sure, you mentioned Nagel, can we exclude the possibility that there isn't something it's like to be a planet?
No, I absolutely would not exclude that. I think it's possible there is something it's like to, and I'm not even like hostile to that idea. What I want to be careful of is taking the leap into like a self-consciousness or
Right.
that reflective kind of thing. Because what I'm always happy with, right? Because what we always want to do when we start down this road is sometimes we want to go to ultimate questions, right? We want to ask about the consciousness of the universe or whatever, which, I totally understand why people want to go there. But again, that's where it comes to the silence, right? And this is from my experience as doing Buddhist
Zen
practice.
meditator, right?
Yeah, at some point it's just silence, and there's not. And again, that's why poetry, like some of these ultimate questions, are not really amenable to science, right? That's not what science was built for. And understanding when we get to the horizon of those is very important. Like what I want a science that knows when to self-destruct, right? I want a science that understands when it's gotten to that boundary between the expressible and the inexpressible and says, whoa, that's as far as we're going with this kind of method. If you want to go further, go see a play, go read Shakespeare, go do a 6-day, meditation retreat, read Dogen, the 13th century Zen, philosopher.
Well,
You're going to need to use other tools to try and get to the bottom of the barrel. And it will be silence. You'll have to penetrate the silence. Science is not good at penetrating silence.
now, coming back to yours and Sarah's work on these levels, alongside the intelligent planetary process model, you've got this idea about the way that intelligence can develop over time, starting as immature and so unstable and unsustainable, and then evolving towards maturity. So, can you just take us through the levels of that development, starting billions of years ago with our immature biosphere, and then stretching right up today with our immature technosphere, totally
Right.
out of harmony with the biosphere and unsustainable, and hopefully well into the future when we can eventually
Fingers
harmonize.
crossed.
Yes, just, hopefully before it's too late.
Yeah. So, and it's interesting because that then goes, when we come to the end of this discussion, we'll get to like how many civilizations are there out there? Because, our idea is that if we don't make that transition to a mature technosphere, which we're about to define, that, you don't go on. And so every civilization that makes it, that becomes long lived, has to make this transition.
Amazing.
Okay. So let's go back. When life first formed, whatever was going on with that, there wasn't a lot of it, right? Life first forms, and there's not, in the beginning, there is not the feedback webs with the geospheres. They haven't been established yet. Like that takes time. You have to have enough life. So one way of categorizing life on a planetary scale is what's called net primary productivity. It's just basically how many sugar molecules, how much sunlight is being turned into sugar molecules. And so it was a fraction of what we have today. So you didn't have, early on in what's called the Archean eon, the Earth has, I think, 5 eons. Early on, when life formed, life was too thin on the ground to really start establishing those feedbacks that could exert controls on the chemical composition of the atmosphere, on the flows of nutrients, rainfall, things like that. But as time goes on, as the biosphere, as you get more life, and as the life evolves and starts to fill niches, life and that open-endedness, that creativity, exploiting every opportunity to make more life, to make more sugars, to make more life, then you start developing those feedback webs. Think of it as a dense network of interconnection with the abiotic, the non-biological parts of the planet. When that happens, and you begin to exert Gaian controls, that's when we would say you've reached a state of maturity, right? And it's the maturity that allows the biosphere to endure billions of years, right? Which is phenomenal. It's phenomenal that the planet has undergone some amazing catastrophes. As we know, there's been 5 mass extinctions. Biosphere is still here, right? And that's because you had these feedbacks which allowed the biosphere to respond. So that's what we call maturity. So about 200 years ago, it's hard to say where really it starts, but certainly the technosphere, that could push back, that could change the biosphere and the geosphere, that emerges somewhere in the mid 1800s, right? We crossed the line of about 1 billion human beings, I think in like 1850. And it's our energy harvesting, just like, the biosphere harvests energy from the sun. We're harvesting energy from rivers, from burning trees, which is secondary from the sun, or when we discover fossil fuels, from burning coal or fuel or oil, which is also secondary because originally that was all came from the sun. So the technosphere, which is the sum total of all of the technological systems and the methods of control, the bureaucracies that make this modern civilization. It is immature. It is immature in the sense that the early biosphere was immature. It's not exerting controls for its own benefit, right? It's not autopoietic. It is not self-creating and self-maintaining. It's self-creating, we're creating it, but it's not self-maintaining. We're actually destroying the conditions that we need for it to be able to maintain. So the idea is that you will not become a long-lived technological civilization. You will not have a long-lived technosphere until you become mature. You're not going to be around for a million, 10 million years unless you figure out how to do what the biosphere did. So the biosphere offers us a model for what planetary intelligence, i.e., an autopoietic system, looks like.
Okay, great. So, having placed ourselves on an evolutionary scale somewhere between immature biosphere and mature technosphere, now we can start to imagine other planets out there, exoplanets, as you call them in your field, that have a life either behind us or ahead of us on that curve. And you cover this topic in great detail in one of your most recent books, The Little Book of Aliens, which faces this ancient question of whether we're an isolated freak accident in the universe or if, in fact, life is common. And it brings us to the famous field, the search for extraterrestrial intelligence, or SETI, as it's known. Became fashionable in the 1950s after the rash of UFO reports in the late 40s. But before we get on to how your ideas and the field of exoplanet research, which you're right at the center of, is altering the sort of SETI research paradigm, and by means of introducing your book, give us a little bit of context about SETI. So maybe we can start with the Drake equation and why that was such an important step in our ability to analyze the probabilities of life elsewhere.
Yeah, it's a great question. The thing is that this question of are we alone is like as old as the hills. As I say in the book, you can see, Aristotle and Democritus, beating each other up over it. Not they weren't alive at the same time, but in their writings. So people have always wondered about this, but there was never anything to do. There was never any science you could apply to it. Like, how would you even, study this scientifically? But by the 1950s, we had started to develop technologies, like particularly radio astronomy, that would allow us to actually, try and think about this. And it was still kind of out there, but it was Frank Drake in 1958, who was a young postdoc who just is at one of the new radio observatories that the United States is building, and says, "Hey, let me, look at a couple of stars and look for signals that are clearly not natural." And you have to go through, what do you mean by not natural? But things that just look really artificial that nature wouldn't produce. So he does this experiment in 1959 or 1960, I think it is. It's called Project Ozma, and named after the princess in the Oz books, because he was a big fan. And he looks at two stars, doesn't find anything, but the press finds out, and it ignites this, amazing interest in, like, oh, can we find life elsewhere? And that was the beginning of the search for extraterrestrial intelligence, or SETI. And he sort of thought, Drake was like, everybody's going to laugh at me. He was looking behind his back to see who was going to be making fun of him. But instead, he gets a call from the government, which wants to have a meeting on interstellar communications, right? So they're like, "Hey, could you organize this meeting?" And he's like, "Okay." So who else to invite? So you end up with like 8 guys, no women, because there obviously were women thinking about this, but they weren't allowed in. And there's a part of the story is a young Carl Sagan is also one of the invitees, and so they have this meeting, and the night before the meeting, Drake is like, "I need an agenda. Like, what are we going to talk about? How are we even going to think about this?" And what he does is he writes down an equation which really breaks the problem of how many intelligent civilizations there are out there, which is really kind of the fundamental issue if you're going to go look, into 7 sub-problems. That have to do with the evolution of stars, the presence of planets, the ability of planets to host life. Like, are they in the right place in their orbits, neither too hot nor too cold to host life, et cetera, et cetera. There's 7 of these sub-problems. And that becomes the Drake equation. And the way he broke the problem up becomes sort of the roadmap, because nobody had ever thought of this systematically before. Science can't progress unless it's formulated its own question. You need a good question to be able to get any answers to begin with. So he formulated the sub questions that you would have to sequentially answer to get to the point of knowing how many intelligent civilizations there were out there. And the amazing thing about this, so that became the roadmap. And we'll get to where we are right now in a minute. But the important thing to understand is that SETI was always treated as a little kooky, right? It was always marginal. There were some, a few really good scientists who were involved in it. Frank Drake, Jill Tarter, hero of the field. But, it never had a lot of funding. Congress a bunch of times, whacked on it because of it was never interested in UFOs, but it got associated, in the minds of some congressmen. So in the 90s, NASA was not allowed to fund anything SETI-wise. So there was a long winter where there was no SETI. And one thing that's very important to understand is SETI never had enough money to actually do large searches, right? So people have this idea that every night astronomers are out there searching the sky for alien signals. Nobody's ever looked anywhere. Like a friend of mine, a colleague, Jason Wright, did a study where they looked at all the SETI searches that have ever been done. And if you think of that as the ocean, the question was, how much of the ocean has actually been searched? Like, if we're looking for fish, how much of the ocean have we actually searched for so far? So, how many stars have we looked at for alien life? And it turns out, using the ocean metaphor, we've looked at a hot tub. We've looked at a hot tub worth of water so far. So if you pulled up a hot tub's worth of water from the ocean and there was no fish in it, would you then be like, well, that's it, there's no fish in the ocean? So we just haven't searched. That's why the idea of the famous Fermi paradox, the idea that we've looked and we haven't found, is, pardon my language, bullshit, because we've never looked. So SETI really had a lot of problems as a field. And it's only recently, because in the 1990s, late 1990s, we really started discovering exoplanets, planets orbiting other stars, which we had no idea about. We didn't know whether there were any planets in the galaxy or in the universe other than the ones orbiting the sun. Suddenly in 1995, we found our first exoplanet. And now we know that every star in the sky, when you look up at night, has exoplanets. And that changed everything. And now we're sort of done with that sort of let's laugh at SETI researchers behind their back. And we know how to search for life. We know how to search. We're deep. NASA is deep into searching for biospheres. And now it's become like, well, why wouldn't you search for technospheres? Like, why would you ignore the possibility that life was intelligent? So I'm the principal investigator on the first grant NASA has ever given for looking at exoplanet technosignatures. And our getting this grant kind of helped break the dam where you like, ooh, NASA didn't want to talk about technosignatures because they didn't want to get the Congress to beat them up again. And now sort of like everybody's acknowledged, or at least it's happening. Yeah, technosignatures, of course.
Absolutely. And it's the techno point that I wanted to just zoom in on quickly. As you say, we don't need to go into the Fermi paradox, but what was interesting about what Enrico thought about, obviously it was in the context of nuclear weapons at that time. So he was also thinking about existential risk and the possibility of people wiping themselves out. I mean, what people started to theorize after that was, wait, maybe all of these alien civilizations have wiped themselves out. And I just want to bear that in mind when we move on to Kardashev, the Russian astronomer,
Yeah.
who started to, I think he was probably the first to talk about technosignatures, the possibility that we might be able to find traces of those. But most importantly, he separated the potential advanced civilization into different levels based on the amount of energy they would need to run their advanced technologies. Now, that obviously brought about this whole techno signature theme. How influential was Kardashev at that point? Or are you saying that in a sense it's only coming out now?
It's really only coming out now in a certain sense. I mean, it's true. So uh, you get Drake, in 1960. Kardashev is 64. And before Kardashev, there was a paper by Dyson, the Dyson spheres, right? The Dyson spheres are this idea that like a civilization will to extract maximum energy from their star. They'll build like a giant sphere around their star with solar collectors. So that idea that, we can think about civilizations and how detectable they will be based on how much energy they consume was very early on, right? But so what Kardashev said was like, okay, let's categorize civilizations by their energy use. So a type one would be a planet that uses a civilization that uses all the energy that falls on their planet. Type two would be like Dyson spheres, a civilization that uses all the energy their star produces. And then a type three would be a civilization that uses all the energy that of all the stars in a galaxy. But that was really early on, and you'll notice it was all mega projects, right? Were all these giant, galactic scale or planetary or interplanetary scale engineering. The cool thing about where we are now is that our technology's gotten so good. We've come to understand planets and how they evolve so well. And the biosphere Gaia idea is a big part of this. That we now know how. This is amazing. We know how to look at the atmospheres of planets that are 40 light years away. We can see into their atmospheres. We can see what those atmospheres are made of. And so we can use the chemical compounds in the atmospheres that we can detect as a proxy for whether there's life or whether there's technology. So, for example, if we found oxygen in the atmosphere of a planet like the Earth, we'd be like, there's got to be a biosphere there because if it wasn't a biosphere, all that oxygen would quickly react away. And oxygen will not stay in an Earth like atmosphere unless life is pumping it out continuously.
Mm.
Likewise, if we saw something like chlorofluorocarbons, right, the stuff that we mistakenly burped out in the atmosphere from our refrigerators and our air conditioners, if we saw a chemical like that in the atmosphere, which we could detect, we wrote a paper on this, then you would say like, oh my God, there's technology on that planet. So like, whereas that first generation, those first few years, the only way they could think about it because they had very limited technology was these huge, engineering projects, which maybe no civilization even does for various reasons. But now we can see right into their planets and just sort of watch what's going on their planets. And it's a whole, that's why I don't even use the word SETI anymore. Some people still do. To me, it's technosignatures. That's the name of the field, right? There's biosignatures, which is the search for just biospheres. And then there's technosignatures, and technosignatures are just a subfield of biosignatures, right?
And coming back to this strong theme, particularly on Earth at the moment, about surviving techno adolescence, it's led many astronomers to speculate that we are thousands of times more likely to find artifacts of dead civilizations than existing ones. And this debate was kicked off again after the 2017 sighting of the interstellar object Oumuamua, when Harvard astronomer and previous guest on the show, Avi Loeb, speculated that it could be space junk from a dead civilization. Now, despite the controversy across astronomy and the pushback, he got loads of private funding for his new Galileo project,
Right.
which was an attempt to ensure that both on and off planet, we were working towards harvesting better data on these objects. So when they pass by, we can get clearer deductions about what they actually are. Are you involved in this Galileo project, Adam? And what's your opinion about Avi's passionate pursuit of more data about these potentially archaeological interstellar objects?
Well, I think the Galileo project is great. I'm not involved in it, but I think it's great. I think the idea is more data. You can always use more data, and data that has been correctly gathered. Right. That's the problem with UFOs in general. People take blurry snapshots from cell phones. Like, look, I've got data. It's like that's not how scientists. That's not how science works. If you tried to build a cell phone out of that kind of data, you'd have a brick, right? I think that the Galileo project is a great idea. The Galileo project is mostly oriented towards UFOs and UAPs, but they are also doing they're also very interested in the interstellar objects, as everybody is. Those interstellar objects, whether or not even if they're not, pieces of space junk or even if they're not technosignatures, they are of enormous interest because they're the first interstellar objects passing through the solar system. They're clues to what's happened in other solar systems. So they're very interesting. Avi, I think, Avi's work on technosignatures has been super important. I just feel like I think what the astronomical community, where a lot of that pushback came from, if I can just interpret that, was that Avi kind of bit down hard on some of his conclusions, particularly say that Oumuamua was a technosignature, and there were people who studied comets for their whole lives, which that's not been Avi's field, who were like, Avi, there's a lot better, more reasonable explanations for what this thing is, what Oumuamua is, than an interstellar, piece of technology. And I think the criticism is they didn't feel like he was listening. Like he was not, you can't parachute into somebody else's field and be like, you're all wrong. Here's my idea. You have to listen to what those people say. And I think that's where the criticism came. But I think the idea of getting more data for I deal with UFOs and UAPs in the book, and I'm very skeptical because up to now the data has sucked, so I'm all for getting good data. I'm all for complete transparency, but the idea that we have any evidence right now that is in any way credible that we're being visited by interstellar technologies, I think is that's from a scientific point of view, no.
Well, Avi did mention this, and he did say that following this Director of National Security John Radcliffe's report in 2021, that was very, very clear that they were talking about a population of objects and about the fact that we can never get hold of government data. Like they just won't give it to you. He said that the Galileo project would offer some open source data for science and for the public on UAP observation too. And he just said, let's just put this controversy to bed once and for all, for God's sake, following decades of taboo and ridicule, despite a really significant percentage of genuinely anomalous interactions, often with military situations like the USS Nimitz case that was famously mentioned in the New York Times article in 2017. So, Adam, I'm guessing that you're going to deny that these are of extraterrestrial origin, but you're not denying that they exist, really. Can you talk the listeners through the logic you present in the book about what are the most likely alternative explanations, given the fact that we can be pretty clear now that UAPs do exist?
Yeah, I think, and they have existed for a while, but like I said, the idea, so let's deal with a couple of different things. First of all, like you said, the idea that the military is hiding the secrets. What people need to understand is that goes way back. Like literally, the first UFO sightings, the ones that get attention, is 1947. The first book by a military guy saying there's secrets out there that nobody knows and only I know them is 1953. And of course he points. There was this document that he talked about called the what is it? The assessment of the situation, which nobody's ever been able to find. Right? We said, which in it, clearly said that these things were, and I loved it, of interplanetary origin, right? Because people weren't even thinking interstellar. It shows you, sort of where how these things evolve. But it's like, there have been claims about this forever. I don't think I would be willing to put $1,000 down that like 5 years from now we're in the exact same place. Like it's like the JFK thing. No matter what you produce, somebody's going to be like, you're not really telling the truth. So I just don't think, I think, but again, I'm all for government transparency. If they've got spaceships in the, in the garage, let's see them. And there's this thing also. I think I forgot the name of the guy who was one of the heads of the Pentagon programs, who was really upset when he was talking to intelligence agents who, without, he's questioning them. Where's the, you're claiming that people know that where's your actual data? And it's always like, well, this guy told me. He didn't see it, but he knew somebody who knew somebody who knew somebody who saw it. And he said, like, it's a circular conversation that's been going on for 30 years. Nobody's ever seen anything. Everybody's just heard in the military and the intelligence communities. Those people who are into it, it's always hearsay. And so that's why, I just don't think there's anything, the idea that like, oh, the government knows. When you actually look what's happening, nobody can ever point to like actually seeing the data themselves. But again, if it's there, my God, release it because I want to see it. So about what it is, actually what it is. On first level, I have no idea, right? I mean, because these things in general, the data is not good enough to say much. All you can do is and it's a really small percentage of the cases. I think that's really important, right? So, any credible report that has ever looked at these things, even the most recent ones, puts the number that are truly unexplainable at around 5%, right? So I think we have to sit with that for a moment, right? So the idea that the sky is full of unexplainable phenomena, that's not true. 95, if you had 100 people there telling you, I saw something I couldn't explain, you could go down the list and go, oh, yeah, that one's explainable, that one's explainable, that one's explainable. You'd go down 95 of them, and the last 5, you'd been like, yeah, I can't explain that. But that doesn't mean by saying you can't explain it, there's 2 reasons you can't explain it. One is you didn't even really give me enough data to begin trying to build an explanation. And then there's the really interesting cases where, okay, you have some data, some witnesses, maybe some radar, and that one I can't explain. So, those unexplainable ones are interesting. They should be pursued. But we have to understand that the sky is not full of unexplained things. Most of them can be explained. And especially more recently with there's so much stuff in the sky now, It's amazing how many of these things people are like, I saw something, I couldn't believe it. It was a Mylar balloon, a Mickey Mouse balloon, and then the stuff with drones is a whole other case. But let me just point out one last thing just to close this up. When I did an infamous New York Times op-ed on this subject, like, when it really was getting hot. And I said, the title they used was, I'm a physicist who studies, extraterrestrial civilizations. I'm not impressed by UFOs. When I wrote that, I went and I looked at the community of people who are military and intelligence, do signals intelligence, or SIGINT or EINT, electronic signals intelligence. And the amazing thing about that, none of them were talking in all their blogs and such, were talking about aliens. They were taught, this is where I learned the word. They were talking about peer state adversaries. And their idea was like, look, if you want to learn your enemy's intelligence gathering capacities, if you want to learn what kind of the suite of electronic detection capacities on a fighter jet, throw something up there, even with a simple drone, that is going to look is going to look weird, is going to look like it's interesting. And then what your adversary is going to do is going to crank up their radars and crank up and then you'll be able to soak up all of those signals and know exactly what's going on. So they all thought their idea was Russia, China, Iran, even with simple drone technologies, would be able to fake what looked like UFOs or UAPs behaving in really crazy ways in order to soak up. And there's lots of examples in history of America doing this to Russia in, like, say, 1960. Russia had built this amazing new radar facility. We didn't understand what it could do. And so we spoofed a signal into it to get them to crank it up so we could figure out what it was. So I have to take a guess. That's what I'm going to guess. And so many of these things are around military bases.
And I would have loved to have time to get into some of these observables with you from a physics point of view. They're so fascinating. Interesting phenomena like no heat signature or exhaust, changing directions at 90 degrees at sort of Mach 8, just extraordinary performances that we would give our left leg to understand how they're doing this. And of course, they are.
Wait, can I just point out, though, like, we don't actually, there's no actual evidence that they've done that, right? What you get is you get pilots saying, I saw it turning away, but, that I've never seen before. But that's not a measurement of a Mach 5. Pilots, personal testimony, even of trained observers, they've shown this a
they've
million
got
times.
that on radar as well, Adam.
No, they do not have. There's no radar data. There's no radar data that you can go get that will show you that, right? So and it's amazing. Remember, like, there's only really 3 videos that get processed over and over again that have been released. That's not raw data, right? Those we don't know anything about those instruments. And here's the thing. So now this is controversial, but there was a scientist who looked at the readings. I think it was the Go Fast one, where it seems to be zooming right over the ocean at, like, incredible speeds. So what he did is he looked at the numbers being read off on the screen on that video. And what he found out, it was actually at 30,000 degrees, 30,000 feet. And it was moving at not, 300,000 miles an hour, but at 40 kilometers an hour, which is wind speed. So, there is no
lots
hard
of ways.
data, that anybody, would really take. Now, there is that paper, I can't remember the name, who tried to use, those readings to try and do, to try and get some sense of what the accelerations were. And that was like a first cut, but it was so raw that, like, it's not enough to really take seriously. I'll have to say, though, I would like to see that paper tried to be reproduced, because it was an honest attempt to get the first cut at it. But there's no way that you would claim that what was in that paper was, hard and fast. It was a first shot at it.
Well, it'll be interesting to find out if efforts like Avi's will come out with some data that we can actually finally analyze properly.
Yeah. I hope so.
Just to close, Adam, because I know you got to go. I just wanted to close by heading back to a great passion that you share with your co-author, Marcelo Gleiser, which is this pushback against the romanticization of space colonization. The plan Bs of Mars and rotating habitats, they may seem like a sort of futurist wet dream, and both you and I are serious futurists. We do love our sci-fi, so we could be drawn into this as well. But this romanticization, this sort of coolness of sci-fi has really had the unintentional effect of moving focus away from the need to maintain the viability of living here on Earth.
Yeah.
The greatest billionaires who fund the 2 biggest spacefaring companies could achieve so much for the same price if they just pushed their money into taking care of this place instead. What do you think, Adam? Is this fallout from our culture of futurism and technology so fascinated? What's the consequence of this?
Well, I do actually. Marcel and I don't entirely agree on this, because I'm a much bigger space nerd than he is, on some level. Like, I watched every Star Trek episode, the original series, probably 40 times when I was growing up. Like, I'm a serious, like, well, as you can tell from my background here, like, I am all in when it comes to, the settlement of the solar system. But I think that's the prize that you win if you deal with climate change, right? Because we will not have autopoietic Mars, for 100,000 years or thousands of years, right? The Earth is the only place you can live. There's no plan B. There's no settling the solar system without a viable Earth. So while I'm very, 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 very excited about the settlement of the solar system, and I'm ready to go any moment, my favorite show is The Expanse. Do you know The Expanse?
No,
Um,
but I shall be referencing it for the listeners. I'm
oh,
watching it.
it is awesome. It is because it takes place about 300 years from now in a settled solar system. And, you know, it's just the science is so accurate. The story as an actor, you know, really the acting is really great. You'd really appreciate. But, you know, one of the points it makes is that, you know, no Earth, no, you know, if Earth were to collapse, the whole solar system would collapse. So, you know, there's no plan B. And you know, the idea that Elon Musk is going to create a colony on Mars that is going to ensure the survival of humanity, yeah, good luck with that. So yeah, no, I think we have the Earth. The Earth is the most important planet for us in the universe, and you know, Project One is to take care of it. But I do think we can do this. I think we can do both at the same time. And in fact, in some sense, by pushing outward, we will also learn more about how fragile, or not how the Earth works. Fragile for us, like I, you know, because one of my things I've always said is, you know, the Earth is not a fuzzy bunny, right? Our project is not to save the Earth. The biosphere will be fine. It's human civilization that's up for grabs, right? The planet will just move on without us and create new conditions for new forms of life, but leave us behind. So if we want the Earth to maintain its habitability for us, then that's the central concern.
Well, listeners, we must raise a glass to our ability to come to technological adolescence and on into adulthood and actually finally become mature. Very, very quickly, Adam, what do you think are the missing ingredients to bring us to technosphere maturity?
I really think, you know, it's funny, this is good, brings us back to where we started. What we need is a different vision of nature. Like our imagination of what nature is and our place in it is very much a product of what emerged out of the Enlightenment. And, you know, obviously there were some good things about it, but particularly it was this view of nature that separated us from nature. We were different from nature. And, you know, the political economy that we built out of that is the one that just can't, you know, it's going to eat everything on the planet just to produce the next, you know, gadget. So it's really it's how we imagine what nature is and where we are in it. That without that there will be no mature technosphere, because it's about reintegrating ourselves back into the biosphere.
Adam Frank, thank you so much for your time. Listeners, you must go out, get the get the blind spot, get the little book of aliens. Adam Frank, thank you for your time.
Thank you. This was fun. I really appreciated it.